Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 26, part A, and we are into part 4 of nested designs. So let's go ahead and get started. We need to estimate our parameters so we can build confidence intervals. Here's our parameters: mu plus tau I, sigma e squared, and sigma b nested within a squared. And we've given the point estimate, so for mu, of course, it's y dot 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 bar, and this is unbiased. For mu plus tau I, it's yi dot dot bar, that's unbiased. Again, all of these are unbiased, so the point estimate for sigma e squared is MSE. And now here is the one that's a little more complicated. And so for sigma b nested within A, it has to be ms b nested within A minus MSE all divided by n. And so let's talk about the standard error of these estimates for the first two, because they're means. We don't have a standard error estimates for confidence intervals for variance components, because it uses a chi-squared distribution, which is not symmetrical. So we have to use a different, we have to use that chi-squared formula, if you will, for confidence intervals here. Okay, so what we have is we have, for mu, we have the square root, because it's the standard error, so it's the square root of sigma hat e squared plus n times sigma hat b nested within A squared divided by A times B times n. For tau plus mu I, we have the square root of sigma hat e squared plus n times sigma b nested within A squared. So it's the same first term, but now we divide it by b times n, and we take the square root of the whole quantity. Notice down here that when I look at sigma hat e squared plus n sigma hat b nested within A squared, that's MSE for this. And then if you remember, we said that this is estimated by MSE or MSB nested within A minus MSE. So all of this reduces to just MSB. Okay? So I could write this as the square root of MS, and that's nested within A, MSB nested within A divided by A times B times N. And this one would be MSB nested within A divided by BN. Okay? And our textbook writes it that way, but I think that's hiding something that is important. I think it is important to spell this out, but obviously that's just my opinion. So now let's look at so we have the standard error. So now let's look at the confidence intervals. For mu, we have y dot 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 bar plus or minus t alpha over 2 and the degrees of freedom from our error. And if you remember, this is A times B times n minus 1, right? And for our example, it was 60, okay? And so we have MSB nested within A divided by ABN in the square root. And for mu plus tau I, we have y I dot dot bar plus or minus, again, the same t critical value. Everything's the same, except here we're dividing by b times n instead of a times b times n. And instead of using y dot 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 bar, we're using yi dot dot bar. So very similar. So please don't get them mixed up. But of course, we're going to let the computer do the calculations for us, so that should take some of the error out of that. Okay. Now let's talk about the confidence intervals for these variance components. Okay. So for the sigma squared E, we have the formula, if you will, for a variance confidence interval. We have the numerator, and in this case it's AB n minus 1, that's the degrees of freedom, times MSE. Now if MSE, I want to remind you that MSE is equal to SSE divided by the degrees of freedom for the error. And boy, that's messy. I just wrote it and I can't read it. Let me clean that up. Okay, whoops. And that's the problem. I'm using my iPad, and sometimes when I lay my hand on it, it changes things. So MSE is equal to SSE divided by the degrees of freedom of E. So this is the degrees of freedom of E. So if I take that times MSE, it cancels out and I get SSE. So this numerator, this whole numerator, let me clean that up a little bit. This whole numerator is SSE, and so is this one. So we could write this more simply as SSE, okay? And we're dividing by the chi-squared. Here it's 1 minus alpha over, oh, and I've got that reversed. Lovely. Okay, so this is alpha over 2. We always take the biggest one and divide by it here, and this will be 1 minus alpha over 2. So I'll correct my notes and post them so that you don't have to correct all this. You can just write it down correctly the first time. And I've got the same here. I was consistent, that's for sure. But unfortunately, consistently wrong. Okay, so the confidence interval is, for the first one, for sigma e squared, is SSE divided by the chi-squared, alpha over 2, and the degrees of freedom for MSE, which is AB times n minus 1. And the only difference for the upper confidence interval limit is that we have 1 minus alpha over 2 instead of alpha over 2 for the probability for the chi-squared statistic. And then likewise, you'll see that here for the sigma b nested within a squared, we have SSB nested within a divided by n. Here's something, make sure you notice this is an n times the chi-squared, and now it'll be the degrees of freedom of MSBA, right? So a times b minus 1. And so likewise here, the only difference is that in the denominator, instead of alpha over 2, we have 1 minus alpha over 2. And now, for this last one, we have a times b minus 1 times MSB nested within a, and that is the degrees of freedom for, yep, so that's the degrees of freedom. So we end up with this, in other words, these two are almost the same except for this n here, and you can't see it now. Except for this n, these two are the same. So the only difference is there's no n here, okay? So everything else is the same, which is interesting. So, but we don't want to have to do the math to show that, okay? It's a little messy. All right. We can also create confidence intervals under the unbalanced design. Again, we'll let the computer do that for us. I don't want to write those messy equations. It would take up a couple of pages here because they get very long. Okay. So it's interesting. I don't believe our book talks about this, but other textbooks do. The efficiency of an experimental design is often judged in terms of the variance of the treatment mean. The smaller the variance of the treatment mean, the more efficient the design. And efficiency of design is something we should consider, all right? We have computers, so in this case, we're not redoing the analysis with a different sample design, but we can say if we kept everything the same, so all the estimates were the same, and we changed the design, which one would be more efficient? Okay, so first we have to figure out the treatment mean, the variance of the treatment mean, yi dot bar. And we've already got that in the table, and it tells us that it's not in the table. We've already done that before, and we found that it's sigma E hat squared plus n times sigma B A hat squared, all divided by B times n. And so from our ANOVA analysis, we'd take MSE plus 4 times MSB divided by 6 times 4. There were 6 leaves, so 4 trees and 6 leaves. And so we end up with about 1.143. That's the design of the actual experiment. Now, if we do this, we may say, well, would it have been better to, instead of using 6 trees and 4 leaves, what if we'd used, 4 trees and 6 leaves, what if we'd used 5 trees and then just 4 leaves from each tree? And that might be easier for us to do because it's easy to spray the trees. It's much more difficult for us to climb up the tree, randomly select a leaf and climb all over the tree 6 times rather than 4 times. Okay, so this could be a lot more efficient in terms of labor. So what would happen? So if we keep all of our estimates the same, but now instead of 4 now we have, I think I wrote that down wrong, we have 5. This should be 5 trees here. And when we do this, and we have 4 times 5 here, and we end up with 0.950. This is smaller, so this would be a more efficient design. But that's a big assumption. It's not a big assumption, but it is an assumption. Basically, we'd have to have the same estimates for MSE and MSB nested within A. Okay. So as I mentioned earlier, the design in this chapter or section is called a 2-stage nested design, as well as a nested or a hierarchical design. Okay. Specifically, we looked at the case where factor A, spray, was fixed, and our nested factor B was random. So we had a mixed model. Now let's look at a completely fixed effects and a completely random. And another word for random effects you may read in books is a variable effects model. So random effects, variable effects means the same thing. Okay, so if we have factors A and B fixed, our model is going to look exactly the same here. But now we have 2 fixed effects factors, so we have 2 assumptions of these effects adding up to 0. So the sum of the tau i's is 0, the sum of the betas are 0. As I alluded to earlier, we now have, because they're fixed, our null stays the same as we had before. All the tau i's are equal to 0 versus, they're equal to the, that should be tau j. All of them are the same versus that at least one pair are different. Our test statistics, the same that we've seen in the previous ANOVA table, MSA divided by, it's different. It's going to be MSA divided by MSE. And so our degrees of freedom in the numerator change. So completely different for the fully fixed effects. And then this one stays the same. So we have MSB nested within A divided by MSE, and that's testing. But now instead of testing the variance is equal to 0, that's random, we're not doing that. We're now testing that those beta, the effects of the nested factor, that those are all 0, or I should say that they are all the same. Beta I j prime, that they are all the same, against that at least one are different. Okay. So we would take the same F statistic here, MSB within A over MSE. But now, let's, and so I've told you how the critical value is going to change based on the degrees of freedom, right? Okay. Now, both factors being random, now our null for the A factor is sigma A squared equals 0 versus it's greater than 0. Now we go back to MSA over MSB nested within A, and this would be the same one we had for the mixed. And then F of B nested within A, the null hypothesis is different. It's sigma B nested within A is sigma squared B nested within A is equal to 0 versus it's positive. And so this one's always MSB divided by MSE. Okay. For diagnostics, we're going to do the same type of diagnostics that we would do in the one-way ANOVA. All right, that's it for this video. If you have questions, please make sure you come to virtual office hours. If you need help prior to office hours, by all means email me. But when you email me, if it's about a problem, then email me what the problem is, because I may not have it available, and then your work on that problem so far. If it's code, then by all means send me a copy of the code, and in the email tell me where you're having the problem and that you need help. And I will get back to you as soon as it's possible. Please take care of yourself and stay safe, because we want to see you here next time.